Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing, testing, testing. Testing, 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 testing on YouTube. Testing, testing, testing. All right. Testing on YouTube. Working on YouTube. What if I use this deep voice the entire stream? Would I get more views if I use my deep voice? What if I used a high voice instead? Would I get more views like that? How's it going, Faisal? How's it going, Sarah? I'm gonna get started here in a second. We just gotta wait for the X stream to start. Let me spit out this gum. Mama SC, how's it going? QD, how's it going? Anestis, how's it going? This is going to be a good one. I'm excited about it. All right, we should be live any second now. Got the multi-stream working. How's it going, Ryan? How's it going, Satish? How's it going, different Ryan? Two different Ryans. Interesting to see. All right, I think we're live on X. Let's confirm that it's working. Are we live on X? Are we live on X? Are we live on X? I think we're live. All right, perfect. Let's get this started. All right, everybody. We got a good one for you today. This one's just called Q-Star. You know, maybe the worst name for SEO because it literally just has a star in the name of the video and the name of the stream. So in terms of SEO, this might literally get filtered out, but we'll see what happens. What is Q-Star, guys? What is this? If you've been living under a rock, maybe you're not super involved in the AI world, this is what Q-Star is. So Q-Star is a rumor of a specific method or technique or algorithm that OpenAI used to get a step function improvement in the current state of AI, but we don't know yet, right? So here I searched for Q-Star OpenAI on Google News, and you can see all the different headlines here, unpacking the hype, hinting at the true nature of the shadowy Q-Star project. Sam Altman shuts down Q-Star questions on a podcast. Should we be afraid of Q-Star? The mysterious new AI system. So as you can see, there's a lot of hype, a lot of mystery surrounding Q-Star, but nobody really knows what it is. Or do we actually know what it is? And here I have a Jan LeCun tweet. Please ignore the deluge of complete nonsense about Q-Star. Very Jan LeCun style tweet there. And he gives you the answer. Pretty much every top lab, Facebook AI Research, DeepMind, OpenAI, DeepMind is Google, OpenAI is Microsoft, Facebook AI Research is Meta, is working on that, and some have already published ideas and result. It is likely that Q-Star is OpenAI's attempt at planning. So Jan LeCun here is letting you know that we actually kind of do know what Q-Star is, right? This is basically reinforcement learning and planning, which has been happening for decades. So if you've read a reinforcement learning paper in the past 10 years, you kind of already know what Q-Star is. But we're going to go a little bit deeper than that, right? We kind of dive deep into the streams. And one thing that we're going to dive into is, here I have a Jan LeCun tweet to kind of flavor it. This is a super recent one. This is 59 minutes ago. So he says, agency and planning can't be a wart on top of autoregressive LLMs. It must be an intrinsic property of the architecture. And actually, this tweet right here by Jan LeCun is in direct contradiction to some of his previous work. Jan LeCun, if you've followed him for some time, is actually known for his cake analogy. So he used to have this cake slide that he would show every time he went and gave a talk. And in this cake slide, he was basically saying that once we get to AGI, AGI itself is going to be like a cake, where the majority of the cake by volume is composed of self-supervised learning. And then the reinforcement learning, or the planning component of that, or the kind of Q-star component of that, is just going to be a little cherry on top of the cake, right? So he calls pure reinforcement learning is going to be the cherry, and then self-supervised learning is going to be the majority of the kind of juice behind the intelligence. So he actually is contradicting his cake analogy here by saying that agency and planning can't be a wart. So he calls it a wart on top of autoregressive LLMs. Autoregressive LLMs are trained in a very self-supervised way, right? They're basically doing next token prediction or masking out specific tokens and predicting those. So they're trained in a self-supervised way based on giant internet text data sets, right? So he says RL is not going to be a wart on top of autoregressive LLMs, but then here he is saying that RL is just the cherry on top of the self-supervised learning cake. So I think it's going to be like this, and I have some papers to kind of prove that. So here we have two different papers that we're going to be looking at today. So both of these papers were released 18th of April 2024, just basically this week. The first one here is called Towards Self-Improvement of LLMs via Imagination, Searching, and Criticizing. This is by Tencent AI Lab. Tencent is a Chinese company, so I feel like it's a little sketchy that Chinese AI companies have labs in the US. So like some of the most advanced AI research is being done by Chinese companies where all the researchers are in a lab in America. Right? Like what the fuck is that? But the other paper we're going to be looking at, also released on the 18th of April 2024. This is called From R to Q Star. Your language model is secretly a Q function by Stanford University, which is one of the top tier American universities, from Chelsea Finn as well, who's kind of an RL god. So we do know what Q star is. And according to these two papers, as you're going to see by the end of this stream, RL is just going to be a little cherry on top. And that little cherry on top is going to ultimately lead us to the AGI that is supposedly behind this OpenAI Q star. All right. How's it going? Jay, Hicham, Mama DC, 2ARX, Economic Reality. With Cake Thing, he is talking about JEPA, not autoregressive LLM. The cake predates his JEPA. The cake is really old, the cake analogy. And autoregressive LLMs, I'm saying that they are self-supervised learning, right? So the way we train an autoregressive LLM is with self-supervised learning. And in these papers, they basically take self-supervised pre-trained LLMs and then just add a little cherry on top, which is the RL. I actually prefer when Jan LeCun admits he made errors in the past. I don't think you're ever going to get LeCun to admit he made an error. He's very entertaining. I think he's got good hot takes, but he's kind of notoriously petty, you know? he's got weird, strong opinions, and he's going to argue them on the internet. That's what he loves to do. All right, let's blow my nose and let's get started. All right. So we're going to kind of, this is a lot of stuff to go through. So I'm going to I highlighted stuff specifically, and then we're going to kind of basically go through that. So LLMs right now, large language models, the way people make them perform better is using advanced prompting techniques and fine-tuning with high-quality data. So this fine-tuning with high-quality data, you can actually think of it as this supervised learning step, right? So supervised learning, you have specific answer or target that you're using to push gradients into your model from. So if pre-training for language models is the self-supervised learning, then fine-tuning is basically the supervised learning. So a combination of fine-tuning with high-quality data, right, these instruction tuning data sets that people have, along with advanced prompting techniques like chain of thought, stuff like that, is kind of what people are doing right now to augment large language models' reasoning abilities. However, these approaches are inherently constrained by data availability and quality. So this paper is going to propose a strategy that allows LLMs to refine their outputs and learn from self-assessed rewards, aka self-improvement. So the language model is improving itself, right? Very reinforcement learning sounding. And in this paper, they're going to go straight to the granddaddy of all reinforcement learning successes, which is AlphaGo. And that's why they're going to call it Alpha LLM. So Alpha LLM, which is this paper, is basically going to be AlphaGo, but applied to language models. So they're just putting that little cherry on top of the reinforcement learning on top of the language model itself. That's going to involve a couple different things, such as Monte Carlo tree search. And ultimately, Alpha LLM is going to address the unique challenges of combining Monte Carlo tree search with LLM for self-improvement, including data scarcity, the vastness of the search spaces of language tasks, and the subjective nature of feedback in language tasks. So we're going to see how there's differences between the problem in which AlphaGo was deployed and the problem of just general reasoning in natural language that make it a little bit difficult to apply, but not impossible to apply, right? And that is why we're going to get results, right? If it wasn't possible to apply kind of this RL kind of planning, MCTS flavored stuff to language models, then these papers wouldn't exist. But the fact that these papers exist shows the potential for self-improvement in LLMs. All right. If you're not familiar with AlphaGo, I highly recommend you go on YouTube and watch AlphaGo. There's a documentary that basically shows you behind the scenes, and then it kind of shows you the lead up to this match. This guy here, this is like the Go champion. Go is basically like kind of like chess. And then this guy is just playing for the computer. So even though we had AlphaGo was a reinforcement learning system that was superhuman at the game of Go, it literally couldn't pick up the pieces. So picking up and moving the pieces on a board with a robotic arm would have been so much cooler. But that's a difficult enough problem that they just had this guy sit in and then just kind of grab the pieces and move it. But he's largely just executing the moves that the AI is telling him. And you can find the link to that here. So all the links that I go to, all the different pages and things that it references, the pictures, you can find them here. I have a GitHub page called Docs. So go on there, and here is all the links if you're interested in that. Definitely check out that AlphaGo documentary on YouTube if you haven't seen it. Very inspiring. All right, so we're going to keep scrolling down. Here they have a little thing. We'll go back to that. Search algorithms, such as Monte Carlo tree search, have enabled models to learn from self-play and achieve human parity or even surpass human performance in complex tasks such as the game of Go. AlphaGo uses imitation learning on expert data, which allows it to simulate human-like strategies. So imitation learning on expert data means that they have expert-level games of Go, and you can train on those expert-level games in kind of more of a supervised way, right? Where you're saying, okay, in this situation, this is what the human expert did. So if we train our model to kind of emulate that or imitate that, then ultimately we're going to end up with a model that basically emulates or is as good as an expert human. But we want to go beyond that, right? We want a model that is superhuman, right? And you're never going to get to something that's superhuman if you're just training on human level data. So in order to get that extra superhuman performance, you're going to have to do reinforcement learning on self-play, which fosters the emergence of novel tactics that surpass human capabilities. And reinforcement learning on self-play is going to involve the exploration of potential moves through statistical sampling of the large search space. All right, so what is statistical sampling of the large search space and search algorithms such as Monte Carlo tree search? What does that mean, right? Maybe you're not familiar with reinforcement learning. Here I have a simple search space. So this is the problem of tic-tac-toe, I think this game is usually called. But this is a game where you're basically alternating turns, and there's 9 positions on a board, and then you're basically putting a token down, somebody else puts a little token down, and then ultimately you try to get 3 in a row, right? And the thing with this problem is it's a very simple problem, right? There's only 9 positions on this board, so you can literally enumerate all possible games in this tree. So this is a tree that starts with specific nodes, and then you can take this move, and then they take this move, and then you can take this move, and then they take this move, right? And because this game is so simple, right? It's just literally 9 positions, and there's only 2 players, and they alternate, and they put positions on the thing. you can enumerate all of them, right? So the search space, right, for that board is very small. The action space is very small. And the bigger the search space and the bigger the action space, the more complicated doing reinforcement learning becomes. So doing reinforcement learning on a Go board game, right, such as this one, is a lot more difficult because the Go board game is a lot bigger, but it's still doable, right? You can still kind of reasonably search the space of all possible actions and all possible states of a Go board. Once you try to do that to language, that's when it becomes kind of almost impossibly difficult, right? Because now you're at each individual token that you're auto-regressively predicting, there's like 30,000 possible tokens that you can output, right? And in a paragraph of text, that now you're talking about a specific trajectory of tokens. That's a huge search space, right? So how are you going to explore that search space effectively? And that's where pretty much everyone is getting stuck, right? That's where every top lab working on applying planning and reinforcement learning to language models, they're kind of getting stuck because they're really, it's a massive search space and you need accurate and unambiguous environment feedback, right? So another one of the reasons that self-play works so well in Go is because the direct and accurate feedback of a win or a loss offers a clear and unequivocal learning signal. So basically, in a game of Go or in a game of tic-tac-toe, you know who wins, right? You know exactly who wins and exactly who loses. So you can always say, okay, well, the person who won, their actions and their specific policy that they were using to pick those actions is better than the ones that the person who lost is, right? So you can have AIs play each other, and then when you say which AI won, you can answer that question objectively, and it's very easy to derive a reward signal from that. But that's not as clear when you're dealing in natural language, right? So like if someone gives you an answer to if you ask a question to a language model and it gives you an answer that's a sentence, you don't have a way to basically evaluate whether that sentence was a win or a loss, right? It's a lot more fuzzy, and the win or loss, like very clear signal, is not there for natural language. Okay. So let's keep going. We scroll down to the usually these introduction sections are a little bit of a waste of time, so we're going to scroll down to the bottom of the introduction section where they give you the exact kind of bulleted list of what this paper does, what the contributions are. And in this paper, they're going to be forming an effective self-improving loop, so a self-play loop that improves a language model. They're going to start with a Llama 270B, so just a generic kind of open source language model. Obviously, there's already Llama 3s, but this is Llama 2 because the work for this was done months ago, right? Alpha LLM can improve its performance from 57 to 92 on GSM-8K and from 20 to 51 on math. So that's no joke. We're talking about multiple, like 10 percentage points. You know, like people will publish papers on just like a little technique that squeezes out an extra 1 or 2 points on these benchmarks. And here they're increasing the scores by like 40. Or like 30, which is a lot. So a self-play loop that gets Llama 270B to perform comparably to GPT-4. So this is real. This is real results using RL as the cherry on top of a self-supervised kind of autoregressive LLM such as Llama 270B. They're going to examine the inherent challenges in harnessing AlphaGo self-learning for LLMs. As we described before, you're going to have a issue with the complexity of the search space because natural language is very large. You're going to have a data scarcity issue because you don't have a bunch of expert games like in Go. And you're going to have to deal with this nuanced nature of feedback, right? How are you going to get a reward signal when you don't have that win or lose at the end of the game? They introduced Alpha LLM, an imagination searching criticizing framework without the need for additional annotations. Annotations there refers to, usually in supervised learning, you are annotating a piece of input to have a specific output. So you're in an object detection case, for example, you have an image and then someone's annotating that image and saying, this is the object in this image. And then you can perform supervised learning and say, okay, well, find the bounding box for this object because I know what the ground truth bounding box is, right? But here you don't actually know what the ground truth or what the best response to a specific question was, right? So if you had to rely on annotations, then we'd all be screwed because we're going to have to wait for hundreds and hundreds of people to label hundreds and hundreds of thousands of stuff, which is kind of what OpenAI is doing with their RLHF, right? They basically have these farms of people that are sitting there comparing responses and saying, this is a good response, this is a bad response, this is a good response, this is a bad response. And anything that relies on annotated data like that is going to be very slow because you need to annotate the data. So that supervised learning, you're not going to be able to get as much juice out of that. You need to figure out some kind of self-play loop, which is going to allow you to go beyond that performance. Okay, so they're going to call this MCTS decoding, which is basically kind of like a beam search where you're basically, as you're autoregressively predicting tokens, you're not just greedily picking the next token based on what your logits are, right? Normally, when you're running a language model in inference mode, the output is basically going to be a set of logits, or you could think of it like a probability for each of the different tokens in your vocabulary, right? So there's like a limited vocabulary of tokens that your LLM can output, and it's picking one of those tokens, and you can pick the token that has the highest score, which would be greedy decoding, or you could do these kind of search-based decoding techniques like beam search or MCTS decoding, where you're kind of looking ahead a little bit, right? You're looking into the possible tokens that could output, going a little bit further than that, seeing which one is actually the best path to take. All right. We're going to scroll through related work sections here as well. Related work, also relatively low signal, unless you're interested in kind of historical context. We propose to leverage the supervision from MCTS for LLM self-improvement, taking the outputs of MCTS to continually train the LLM. This is because the outputs of MCTS are usually much better quality than the standard nucleus sampling, and the large gap ensure that the LLM can self-improve. Okay, so all of this is going to boil down to using MCTS, which is a type of search which you're executing on a tree, right? So you're basically saying, okay, out of all the moves that I could take at this particular point, here's all the moves I can take, and then I'm going to go one level deep past that, and all the moves I could take after that, and then all the moves I can take after that, and which of these little chains of moves is going to be the best for my current state, right? Here's how you would kind of do that for a simple game like this, right? And you can envision a more complicated version of this for the game like Go, right, where it's a much bigger board, and there's many more leaf nodes than there for each individual root node. But for language, it's even more complicated than that, right? Because every single root node has like 30,000 possible leaf nodes, and then every single one of those leaf nodes has another 30,000 possible leaf nodes, just because your action space is 30,000 possible tokens, which is absolutely ginormous. All right, we keep going. All right, so now this is going to be potentially the part where we lose a little bit of you, but like any other reinforcement learning paper, they're going to start off with a preliminary section where they explain reinforcement learning. So I'm going to kind of go through this in relatively quick manner, but maybe for some of you this is new, but for a lot of you this is probably just a review. So a language model is basically a function approximator. You're using a deep neural network to approximate a function. That function that you're trying to approximate is a conditional probability distribution that basically says, given some sequence of input tokens, a sequence is just a bunch of tokens in a row, aka a sentence of words, you're going to generate some response. So here your response is also going to be a sequence of tokens, which is also going to be a sentence or a paragraph or whatever you want, right? And each of those tokens is a token from a predefined vocabulary. So as I keep saying, your tokens are limited to some specific vocabulary. And the policy operates in an autoregressive manner, which basically means that every time it outputs a token, it's using all the previous tokens. And then when it outputs the token after that, it's using the token that it just output and the token that it just output. So it's outputting tokens one at a time, relying solely on the context provided by the previous generated tokens. The policy therefore constitutes a Markov process. So the Markov decision process is kind of the cornerstone inductive bias in reinforcement learning, which is this idea that you have states and you have actions and you transition from states with actions to other states, and then you can have some reward function that is specific to a state and action. So given this state, taking this action is going to have this reward, so you can look at which action gives you the highest reward and then have a policy which kind of tries to pick the best action for a given state, right? And that's called the Markov decision process. And in this paper, they're basically letting you know that you can think of a language model as a reinforcement learning model. That's kind of just picking the best token for a particular context of tokens. Okay, this sets the stage for applying reinforcement learning, which tries to maximize the expected cumulative reward R. The expected cumulative reward R based on some initial dataset D0, which consists of n expert-generated prompt response pairs. So you're starting with some instruction tuning dataset, right? Some annotated dataset, or as Jan LeCun would put it, some supervised learning dataset where your human supplied data is kind of what you're relying on there, right? So you're hoping that the dataset that you're starting from is expert generated. So you have some expert human is telling you this is a good prompt, that's a bad prompt. But then, ultimately, you're going to have a refinement process where you're learning from synthesized prompts and corresponding responses. An advanced search algorithm that's going to navigate the space of possible responses to maximize the expected reward. That search algorithm is going to be your MCTS. The primary challenges is going to be synthesizing suitable prompts, efficiently searching over a vast action space, and obtaining precise feedback. Okay, so here's their definition of MCTS, which is a sampling-based search algorithm. MCTS is basically 4 phases: selection, expansion, evaluation, and backpropagation. And ultimately what it's doing is it's recursively selecting the children from the root node. So they actually have a little diagram here of what MCTS looks like. So you start with some state, right? This might be either the state of a board, right? Such as this, or in the case of a language model, it's like I have a specific sequence of tokens, and then the next token that I can output can be one of these possible tokens. Okay. Out of these possible tokens, let me just pick the first one. And then what are the possible tokens that I can sample from there, right? So you're taking each node, each leaf node, and then expanding it. So you have more leaf nodes. Then you're doing this simulation, which is basically, okay, well, I can kind of simulate what that is. Or here are the possible tokens that I can output there. And the simulation here is basically just being done using a fast rollout policy. The fast rollout policy is just going to be a language model, as we're going to read in this paper. So you're just using a small, kind of shittier language model that's you can evaluate very quickly to roll out in the possible space of future future tokens, right? In AlphaGo, this is a lot easier to do because the action space is a lot more constrained. So doing this kind of tree expansion is a lot easier to simulate because the entire environment of Go is like discretized. So it's very easy to kind of expand out this tree very quickly and then evaluate the potential reward that you're going to get or the value of each of these individual states, right? So once you kind of expand out this tree of here's all the possible things I could do, I'm going to say, okay, out of all these possible things I can do, which one of these things are the most useful to do, right? So you're going to need some notion of, is this useful or not, right? And that's where you're going to have the introduction of a term here called value function. And PRM, ORM, kind of these all fall under the same umbrella of like, I need to know how much better this path is than this path. So I need to have some kind of value, some kind of number, reward, something that tells me how much better each node is than the other one so that I can take the correct path, right? NI and NI are the visit counts for the node. C represents a hyperparameter balancing exploration and exploitation. WI is the average value of all descendant nodes. The tree undergoes expansion. The value of each newly expanded node is estimated with the value function, and then the estimated value is backpropagated to all ancestor nodes. Okay. And that is basically MCTS. Okay. How's everybody doing? Everybody's still following along? Are we all good? Any questions? No questions? All right, let's keep going. So that's the preliminary section. In the preliminary section, they just kind of describe reinforcement learning, MCTS, and now they're going to talk about specifically Alpha LLM, which is their algorithm in their paper. Okay, so Alpha LLM has 2 basic components. It has imagination component, and then it has the efficient search component. So in, for example, Alpha Search, I think it was called. I don't know. This isn't necessarily new, right? Another important thing to realize is that even though I'm presenting these 2 papers here as Q-star, like these type of papers come out constantly, right? So like pretty much we've already reviewed other papers that had very similar ideas to this. And as Jan LeCun kind of put it, like all you got to do is just go look at reinforcement learning right now, and pretty much every other reinforcement learning paper that comes out is like related to language models and doing some kind of similar type of stuff. So it's not like these guys at Tencent figured it all out and everybody else has just been twiddling their thumbs. Everybody's kind of doing the same stuff. I just think that these papers that were released recently, they're just good, and they just show it very clearly kind of where and what Q-star would look like, but it's not like these guys figured it out or something like that. This is just kind of generic RL with LLM papers. Okay. Your efficient search component, which they're going to call NMCTS, is proposed to search high-quality trajectories, and this is going to be, the search is going to be based on the value of each of those trajectories, which is guided by critics. So critics there comes from the reinforcement learning world, where you have this idea of an actor and a critic. The actor is the policy, aka the thing that actually performs the actions, and the critic is the basically another neural network, another function that is being approximated by a deep neural network that is basically tasked with trying to predict the value, or like how good a specific trajectory is. And a trajectory is just like one specific path through this tree of possible futures. Okay. We're going to synthesize data. So in this self-improvement loop, the LLM is synthesizing its own data that you're then going to push gradients back into the LLM, which is the policy. So in reinforcement learning, in deep reinforcement learning, everything was deep neural networks. But now in the modern age of reinforcement learning, we've replaced the generic kind of deep neural networks with transformers and language models. So reinforcement learning is having a resurgence by basically just saying, okay, well, reinforcement learning is still good, but we just need to replace all these deep neural networks with a different type of deep neural network, which is a pre-trained transformer that's been pre-trained on a huge amount of text data, which is kind of the current generation of LLMs that we have. Okay, you're going to have a transformation function G that controls the synthesis process, which can be a learnable function, manually defined heuristic rules, or more what they're going to be doing in this paper, a strong LLM, or the policy model itself equipped with data synthesis instructions. Okay. Option level MCTS. So this is a little trick that they do in this paper where they actually want to think about, okay, well, how granular do you want this to be, right? Do you want this to be token level, sentence level, or what they call option level? All right, so in our little MCTS, right, with a game like Go or a game like tic-tac-toe like this, the granularity of the state and the action and the state and the action is very obvious, right? Your action is going to consist of moves because this is a game where you're sitting there and you're alternating with a person back and forth and back and forth. What you're choosing for your action space and what you're choosing for your state space is really obvious. It's just, okay, one move is an action and the state is just the state of the board before you take a move. But with natural language, it's not as obvious, right? Like, are you just going to do token level? So in token level, each individual token that you output is kind of like one move. So you're kind of thinking about this tree of possible futures as if each individual node is like, okay, I choose next token, and then I could choose the next token, and then I could choose the next token. But this is going to be very, very slow, and it's going to be a very large search space. So as they said before, token level search, where each token is considered an action, you're going to have a substantial vocabulary size, and conducting a deep search in such a vast space becomes increasingly complex as the search space expands exponentially. So to mitigate this, we're going to propose a couple different things, such as sentence level search. Okay, well now, rather than each action being just one token, we're going to have kind of multiple tokens. So you see here, now we have multiple tokens. So we're kind of batching it a little bit. We're still creating this tree and then searching through this tree with our critic and then evaluating the score for each of these different trajectories. But rather than doing it at the token level, which would be a little bit too much work, we're going to do it at the sentence level. So that seems like a better way to do it. Okay. In this paper, they're can actually introduce another layer of complexity on top of that, which is what they call option level. And in option level, you basically pick the granularity. So sometimes it can be tokens and sometimes it can be sentences. And in order to have a variable length there, you're going to introduce a new model, which they call the termination function. I think they mentioned it somewhere here. Yeah, termination function beta. So you're going to have some function that is kind of separate from your language model, or maybe it's an additional little head to your language model that is basically saying, okay, am I done? Is this the end of the sentence, or is this not the end of the sentence? And this termination function basically outputs a single number between 0 and 1, and then you have some threshold, and you say, okay, if that threshold is reached, then I'm going to terminate, and that's going to be the end of this action, and then I can do my next action, which is going to be another sequence of tokens. So this is a nice little trick that they use in order to not get kind of bogged down in the giant potential tree that could come from just using token level search. Okay. How do you get the value function? How does it know the value of the option? That's a question from 2ARX. So normally in deep reinforcement learning, you would have to basically train this value function from scratch. So you would start with an empty neural network, and then you would just play millions and millions of these games of Go. And because you know the winner and the loser of every game, that would slowly over time give you the value at each individual state and taking a certain action, right? But as we're going to see in this paper, they're just going to, for this thing, they're not going to start from scratch. They're actually going to use, so we're going to cheat a little bit, scroll here to the value function. The value function is going to start from a pre-trained language model, right? And that's actually going to maybe lead to the paper here, where the value function is a language model. A language model is a kind of value function. So that's where the value function is going to be coming from. It's going to be coming from a pre-trained language model, which is kind of the key insight of this type of Q-star thinking, is that you can just use these language models as policies. You can just use these language models as value functions, right? And then they benefit from all that general knowledge that they got from that pre-training stage. All right, so we were talking about this option level MCTS. And option level MCTS, just a review of MCTS again, which is those 4 stages. Starting from the root node, we're going to iteratively select the child node. Then the option is sampled using the policy, and its completion is determined with the termination function. Okay, so you're basically picking the possible futures, and the possible futures aren't just limited to individual tokens. They're going to be little batches of tokens, right? Little sequences of tokens, where the length of that sequence is determined by this option model. Okay. Once you do that, you're going to simulate future trajectories. So you're going to add more nodes to your little tree. And then once you add those nodes, you're going to have to figure out the value for each of those nodes. And then you just kind of keep repeating this process. And eventually, the average value of the newly generated node and all of its ancestors is updated using the scaled reward from the evaluation step. So now you're going to push that gradient back and say, okay, I've done this little tree search. I've evaluated all the possible things that I could take. I've figured out which ones are good trajectories, which ones are bad trajectories, which trajectories have a high likelihood of giving me a high reward, which ones have a low likelihood of giving me a high reward. And then I'm going to take that and push the gradients all the way back into the policy. And then the policy will get better at picking the trajectories that have a high reward. All right, this facilitates a deeper search and broader coverage of the search space. They're talking about specifically the kind of option level MCTS, and minimizes the frequency of requesting feedback from functions such as the value model, right? If you had to do it at every single token, you'd have to constantly be calling this value model. If you have your value model is going to be a language model that's loaded on a GPU, your policy is going to be also loaded on a GPU. So you have a lot of different pieces within this reinforcement learning framework, and each of those pieces is a model, right? So if you have to constantly wait, okay, we're going to send something to this model, it's going to evaluate it, and then we're going to use it to go there. And then we're going to send something to this model. Like, you don't want to be constantly waiting for inferences from a bunch of different models. So if you can output a bunch of tokens at once and then send that whole sequence of tokens to the value model, that's going to be a little bit more efficient than sending tokens one at a time to this value model. All right. Unlike token level MCTS with limited action space, the sample space at the option level is exceedingly large with an unlimited number of token combinations. Okay, so this is maybe a problem that we just introduced, right? So we were already talking about how the action space is a little bit too big with these language models, right? Because the language models, they have 30,000 possible tokens. That's a huge ass action space. Once we do this MCTS with the option level search, we've actually just increased the action space, right? Because now we're not talking about the 30,000 possible tokens. We're talking about a variable length sequence of tokens where each token is one of 30,000 possible tokens. So even though we've added some efficiency by doing this option level search, we've actually just completely shot ourselves in the foot in terms of the action space, because the action space and state space is now basically impossibly large. Okay. They're going to have some tricks here, allocating a larger child budget to nodes of higher importance. They have this notion of a branching factor, which is kind of like how many possible futures you can evaluate for each node, right? As you're expanding this tree, you're going to have this idea of an importance of a node, blah, blah, blah. States under the same node can be very similar, causing many unnecessary subtrees, right? So you're expanding out these nodes. Maybe you kind of spend a bunch of time expanding trees that are the same. So in order to do that, you're going to generate a new option from the policy. You're going to use some heuristic function to measure its similarity with existing options. So you're going to have some distance function dist, which is probably also some kind of language model, right? It's just encoding, okay, here's the text for this node and here's the text for this node. Are they actually the same? So I can take those texts, encode them into a vector, look at the cosine similarity between those vectors and determine whether they're very similar nodes or not very similar nodes. So this is very similar to what people do with RAG, right? In retrieval augmented generation, the retrieval part of that involves going to some database and looking up text that is related to the text that you have based on a similarity metric between text, right? Usually embedding vectors. And this is kind of a similar idea where to try to not just pollute your tree of possible futures with repeated nodes, you're going to be using this distance function with some threshold to make sure that each of those different paths that you can take are at least different enough that you're being efficient about your MCTS. Okay. Another trick they're going to have here is what they call fast rollout. So as you're expanding this out, right, in order to expand this tree, you are going to have to evaluate your policy. And if your policy is this big ass model, it's going to be annoying to rapidly expand that. So you're going to have a rapid rollout policy. So a rollout policy that projects future trajectories from a given state. And to do that, you're going to have a smaller, specialized language model as the fast rollout policy. Pi0 would serve as the rollout policy, yet its computational demands render it impractical for the rapid simulation. So you want something that's kind of fast to evaluate. So just kind of a little dumber, maybe a Llama 7B that just goes out there and says, here's all the possible things that I could do given here. I'm going to build this tree out. And because I have these similarity kind of filtering, and I also have this importance-based filtering. So I have some filtering strategies that means that this fast rollout policy, even though it's not quite as good as the real policy, I'll still be able to kind of filter the crap and get a relatively good tree in which to search with my MCTS and then run my value function on that. How does the pre-trained model know the value? If you are basing that on human evaluation, then how can it be better than a human? We'll get to that. We're going to run into the value functions here to ARX. Let's see if there's any other questions. Pre-trained model knows implicit value in its LM, which is replaced. It is no better than the best human. Yeah. Like, you guys are all correct, right? And the intuition that you guys have here is that basically, if you train on human data, you're only going to be as good as the human data, right? So, and we want language models that are superhuman. So how we're going to get to that superhuman level, we need some way of farming reward from the environment, right? That's the kind of way I think about it. In games like AlphaGo and Tic-Tac-Toe, you can farm basically infinite signal from the world because you have this final reward that you can heuristically evaluate, which is winning the game or losing the game. But you don't really have that in natural language. You don't have like a actual true, like, this is exactly good and this is exactly bad. You're kind of relying on these proxies based on expert data sets, or you're limiting it to a specific type of question, which is something that you can evaluate. And actually, that is a little bit of a cheat code. So one of the things that this paper does, which is a little bit of a cheating, is that GSM-8K and math are math, right? So a math question, you can evaluate and say, this is actually the correct answer and this is the wrong answer. So there's a little bit of cheating here in that this technique is only demonstrated to work for things where you can kind of evaluate and know for sure that this answer is better than that answer. So in that way, it's very similar to a game where you have that final signal. But that's actually what I think maybe Q star is. That's maybe what our boy here, Ilya, figured out, right? Maybe, to me, the one thing that I don't see in these papers is how do you get this self-play loop with a language model in a domain that isn't easily evaluated like math or coding, right? Because all the papers we've read up until now, they're only limited to things like math and coding. But how do you get something that's better at just like logically talking about things, right? Or better at reasoning about things, right? Like there's no environment signal to farm from that. But maybe that's what this guy figured out, right? Maybe what this guy figured out is a way to use a pre-trained language model as a value function outside of a domain that is just math and programming. That's my guess. If the hype is real. If the hype is real, that's what Q star is basically Ilya figured out how to use a language model as a Q function in a more generic set of tasks. But if the hype isn't real and Q star is basically just this, but at OpenAI, then all Q star is basically just GPT-4 with better math and programming abilities. Okay. What do you think of grammar-constrained decoding? Maybe with semantically rich functional grammars, we could narrow down the search space. I don't really know much about grammar-constrained decoding. I'm assuming that's some kind of, you have some heuristic evaluation, kind of like value function that tells you whether the grammar is correct or not. Maybe there's a way to kind of get some signal from that, but I imagine at some point you would be limited by kind of the hard-coded, like this is good grammar, this is bad grammar kind of thing. When AI comes up with natural hair regrowth, I'll start believing. Yeah, I don't know why he doesn't shave his head, you know? I feel like you eventually, I'm part of the bald brotherhood, you know? Like, I feel like at some point you got to take pride in just being part of the bald brotherhood, you know? Be okay with it. Like, this look is just so bad. But there's kind of, I've seen this both ways, because sometimes when you have thinning hair like this, you can almost use it in a predatory way, right? So like if you have like, for example, like a very obvious mole on your face or something, or you have some kind of thing that like immediately makes people focus on it, then whenever you're talking to them, they're going to be focusing on that. And they're going to have a hard time kind of listening to what you're saying and kind of, you know, like maybe poking back and criticizing, because they're just sitting there looking at your terrible hairline, right? So I've actually seen that before, where people who have like weird hair situations or like some kind of weird scar or something like that, they can use that to kind of like throw you off and then kind of like dominate the conversation a little bit. So maybe we just think Ilya's autistic and that's why he doesn't even realize that he should just shave his head and join the bald brotherhood. But maybe he's actually literally using that as a technique for kind of dominating conversations by just like having this prominent hairline there. Okay. All right, conspiracy theory over. Let's go into the critics, all right? It is crucial for searching algorithms to have reliable guidance signal towards achieving the end goal. In Alpha LLM, they're going to have three different types of critics. They're going to have a process reward model, PRM, and an outcome reward model, ORM. And actually, we're going to take a little tangent here, and we're literally going to be looking at this paper, Let's Verify Step by Step, by our dear friend Ilya. So, you know, these guys are working on it. They're even publishing papers on it. So as Jan LeCun says, we do know what Q star is. We just don't know whether they got a Q star that is better than everybody else's, or whether the Q star that they have is just what everybody else has, right? But in this RL themed kind of stuff, we have a good definition of ORM and PRM. So I'm going to use this definition here. Two distinct methods for training reward models: outcome supervision and process supervision. Outcome supervised reward models are trained using only the final result of the model's chain of thought, while process-supervised reward models receive feedback for each step in the chain of thought. Okay, so basically what we're learning from this is that the difference between an ORM and the PRM is kind of where are you getting that feedback? Are you getting it at every single token or every single kind of little step in your chain of thought, right? Your chain of thought is whenever your language model says, okay, I'm going to do this, and then 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 this is the final answer, right? Are you getting feedback at every single step, or basically at every single kind of node in the tree? Or are you getting it all the way at the end, kind of like a game, right? In the game, like Go, you don't actually know whether the move is good or not until you get to the very end of the game and someone wins, right? Then you can say, okay, someone won. Now we're going to take that outcome, which is that the person won, and then go all the way back and say, okay, at the very end, they won, so all the things that they took to get to that state are good, versus in this PRM, you're kind of looking at the more granular path it took to get there. Okay. I think I also wanted to show this. No, I think I'll search that later. Okay. Let's go back to our critic. Value function. The value function, v pi phi s, so parameterized by phi, that just basically tells you that this is a neural network. This is a neural network that is associated with a specific policy, so that little pi is the policy, and then this phi right here is the parameters of that neural network. So parameterized by this just tells you that this is some neural network that has some parameters, and those parameters are going to be improved over time using gradient descent, coming from some kind of signal. The reward from a state is the sum of rewards obtained in the future discounted by a factor. So this is kind of, you've heard this a million times in reinforcement learning, but what you're really trying to maximize, what your policy is trying to do, is it's trying to maximize the expected discounted future rewards. So what that means is that it's trying to maximize the reward for a specific action. It's trying to pick the action that gives you the best reward, but the reward for that action is based on the reward of that particular state that you're going to end up on. And the reward of that particular state is based on the reward of the next state and the next state and the next state. The discount factor basically just makes the reward of the future just a little bit less important. So if you can think of the very final reward in a game of Go, that's going to be, okay, that very last step, the one step that you took that won you the game, that's going to have the highest reward. But then the step before that step is going to have a little bit less reward. And the step before that step is going to have a little bit less reward. So that's the kind of idea behind discounting rewards going backwards from the kind of final state. Okay. You have some expert demonstration data set where you have these tuples of just input sequences, output sequences. This is going to be your instruction tuning, right? Those generate some trajectories, or you generate some trajectories, which are given this X, you end up in this O, go to this X, state, observation, action, state, observation, action. We then construct a data set. The value function is optimized by minimizing least squared error. So you have your value function, which is a neural net, which is approximating, is trying to guess what the value is. And then you know the actual value because you actually know who won the game. And then you basically backpropagate from that. In this case, the value function is literally just initialized from the policy. So the value function is the policy with a little multi-layer perceptron on top of it that outputs a scalar. So the value function outputs a single number, right? So the way that they do it is they just take their policy, which is a language model. So it's just a language model that's consuming a bunch of tokens. And then at the very end, they're going to put a little tiny multi-layer perceptron, and that little tiny multi-layer perceptron is just going to output a final number. So the value function, at least one of the value functions that they look at, they have three different value functions here, or three different critics. This one is just going to be the policy with a little MLP that outputs a number, and that number is the estimation of the sum of discounted future rewards. Okay. Then we're going to go into PRM and ORM, which are coming from that this paper here, the Ilya paper. These are largely kind of the same thing, just kind of slightly different. So learning could be inefficient due to delayed and sparse rewards, right? PRM is about your process, so it's a process reward model. So PRM is a function that goes from specific, like each individual part of your trajectory. And much like all the modern reinforcement learning, they're going to formulate PRM as a text generation task. To train the PRM, we initialize it from the policy model as well. So PRM is also a language model and is used the following prompt template. So here is the prompt template for the PRM. A detailed rubric that specifies how to evaluate the step of a task. Right? And then the ORM is going to be basically the same thing, except you're going to do it at the very end. A detailed rubric that specifies how to evaluate the complete trajectory of a task. So basically the difference between PRM and ORM is that you're evaluating each step or evaluating the complete trajectory. Okay, but both of these are initialized from the policy model, which is a language model. All right, now we finally get to the secret sauce, which is this policy self-improvement. All right, so now that you have a policy, which is a language model, now that you have critics or value functions that are telling you how good each individual action and state and trajectories are. Now you can actually combine these two together and do data generation and policy fine-tuning. So your data generation is going to be your MCTS, where you're kind of expanding, using your little fast rollout to look at all the possible trees. And then you're going to be using your little value functions to tell you how good each of those little trees are. And then you're going to actually take steps, eventually get some rewards, and then push gradients all the way back into your policy. And then in that way, improve your policy. Right? And the way that you can think about this is that what you're really doing is you're collecting data sets and then fine-tuning on those data sets, and then collecting more data sets and then fine-tuning on those data sets, which is very similar to what you do in reinforcement learning, for example, in robotics, right? You're using your policy to get a bunch of experience, as they call it. Then that experience will serve as the data set that then is pushed into the policy, and then that new policy is used to gather more experience. So it's kind of this alternating gathering experience or generating sequences of tokens, and then picking the best ones out of those, and then using those to push gradients into the policy, which is then used to then gather more experience, and so on. And that's kind of the self-play virtuous cycle. And hopefully over time, those data sets get higher and higher and higher quality. Right, in the game of Go, each successive kind of self-play iteration results in higher level games and higher level games and higher level games. And at some point, your policy is creating superhuman level games. Right? And that's how you get a superhuman level policy, is that the policy itself is generating the data that is of higher quality than expert level Go games. Right? And that's really the reason that this works, is that we are able, using self-play, to generate Go games that are higher level than this guy's Go games, right? So if you just had every single game that Lee Sedol played, that's the cream of the crop, pinnacle human expert demonstrations. But with self-play, you're basically going a level above that, right? You're figuring out how to create a data set of games that is even higher level than the best human. And if only we could do that for language, right? That's what we really, really want. Can we generate fine-tuning language data sets that are basically better than expert human data sets? And the jury's still out. We don't know 100%. These papers, both of the papers I'm showing you today, only do it in math and coding, because math and coding, you can evaluate and say, yeah, okay, this is a valid piece of code. Yep, this is a valid math. But I suspect that there's a way to do this for just language and logic, right? I think that language has enough structure in it that there's probably some way to basically make something just generically smarter and generate these data sets, these synthetic data sets that are just better in some way. And I know that it's very difficult for us to even try to think about what the fuck that even means. Like, what does it mean to be better at speaking language than the best humans who are, it's like, what does that mean? But I think that there is something there. And that's what I think Q-Star is. I think Ilya figured it out. I think Ilya figured out some way to basically do this in natural language. Okay. All right. Data generation, we have our synthetic prompts. Ultimately, we're creating these trajectories. We want the trajectory that yields the highest critic score on the leaf node for each input question. So the highest critic score, I think they're using basically the weighted combination of these three different value functions, but they probably ablate all of them. But ultimately, right, you want the trajectory that goes through the nodes and gets the highest score based on your value function. We filter out the instances where the corresponding trajectory is not high quality. So again, you have this kind of idea of filtering, because the problem with this is that the search space is so large that you really need to be aggressively filtering in order to explore and find good high quality trajectories. Policy fine-tuning. Once you have that training data DK, then you can simply just fine-tune it as you would normally. Here's your standard kind of loss here, right? Your little log loss. And then you get a new policy. So you just push a gradient based on that data set that you just collected. So you're collecting this data set DK. You're trying to maximize or minimize this loss, which is the expected value of your policy here. And then you push that, get a new policy, theta k plus 1. So you see how that theta k, those are the parameters of the neural network. Theta k becomes theta k plus 1, which means you took one gradient step in your weight space. All right. Experiments. So we're kind of getting to the end of this paper here. What they ultimately got was very good results, but only in the space of coding and math, right? So mathematical reasoning problems where the learning signals are clear, aka the final answer is correct or wrong, such as GSM-8K and math. They're going to compare to GPT-4, GPT 3.5, Anthropic's Claude, Google's Palm 2, Llama, and they're starting from a Llama 2 70B. That's the kind of the base policy that they start from, and they're comparing to Wizard Math, whatever other kind of like I don't know what Wizard Math is, but basically Wizard Math is probably just expert, right? Wizard Math is like, okay, we take a generic language model such as Llama 2, and then we have a data set of supervised like math questions that a human has gone through and said, okay, these are correct, these are expert math questions, and then we just fine tune it on that. Okay. I think there's one extra thing I wanted to show here, chain of thought and PAL. So we're going to take a quick detour to explain both of those terms. So PAL comes from this paper here, Program-Aided Language Models. Prompting methods such as chain of thought employ LLMs for understanding the problem description by decomposing it into steps and then solving each of this step in the problem. So this is what they mean by chain of thought here, right? We employ COT. So COT is basically just that, like explain step by step, right? You literally ask the language model to be a little bit more verbose when it outputs. And then PAL is Program-Aided Language Models, a novel approach that uses LLM to read natural language problems and generate programs as the immediate reasoning steps, but offloads the solution step to a runtime such as a Python interpreter. Okay, so PAL is kind of like, you could think of it like chain of thought, but you're basically saying, okay, write a program that solves this math question. Okay, and because you wrote that program, we can evaluate that program and know, as they said here, whether the final answer is correct or wrong. We can have like a true ground truth here, right? Like the fact that you can actually have a ground truth for math and coding means that that's why you can do this self-play loop for math and coding. Okay. So really they're just fine-tuning here. So they're only training for 3 epochs and with a learning rate of 5 times 10 to the negative 6, which is a really small learning rate, right? So they're not trying to completely overwrite the weights of the Llama 2. They're trying to keep the Llama 2 largely about the same. They're just kind of pushing a little bit of signal in there, right? Just fine-tuning a little bit, little learning rate, just training for 3 epochs, which isn't a lot of time, and the data set isn't very big either. So small amount of epochs with a small data set at a very small learning rate means that the weights of that Llama 2 are largely going to be about the same. It's just a little bit different, right? So it's not like you're kind of pushing this with a massive learning rate and just completely overwriting what the Llama 2 has. Okay, and then obviously the results, as we saw before, is drastic improvements on GSM-8K and math. Alpha LLM demonstrates performance comparable to that of GPT-4, but specifically on math, right? So let's not take their results too much. Here you have the direct results, so we can confirm it for ourselves. GPT-4 with sampling-based decoding gets a score of 92 versus Alpha LLM with this MCTS gets a score of 92. And here the interesting thing, Alpha LLM with a greedy decoding strategy, which means that it's basically just autoregressively picking the token that has the highest score. So this is kind of the most naive way to decode, actually gets not that good of a score. And this is kind of the interesting part, is that you're not making the model that much smarter, right? So here's the Llama 2 70B versus Wizard Math. I guess let's look at this one. Llama 2 70B with supervised fine-tuning. So this is kind of the classic way that you would make a math-specific model now, gets 69. So if you just take a math data set, fine-tune your Llama 2 on that math data set, you're going to bump it by about 10%. And if you take your Alpha LLM, which has been fine-tuned with these smaller synthetic data sets, you're going to get 73, which, it's kind of a little bit better, but it's not that much better. Now, if you take Alpha LLM, and when you're performing inference, right, rather than just kind of greedily picking each individual token as you perform inference, you use the MCTS during inference. So as you're performing inference, you're literally creating these little trees and then going down those little trees and then picking the best one and then going to the next thing and then creating another little tree and then picking the next best thing in that tree and then so on. That's where you actually get the GSM-8K 92 that is comparable to GPT-4. So it's not like we've created a language model that is smarter than GPT-4. We've created a language model and we're using a specific type of decoding or inference strategy that allows us to get to GPT-4 level. Okay. They do a little ablation study. They kind of compare all the different random little tricks that they used, blah, blah, blah. 2 iterations of self-improvement. This is kind of one of the more disappointing parts of this paper. And this was the same kind of situation for, I think there was a meta paper that we read that was also about self-improvement. And in that meta paper of self-improvement, they also only ran it for 2 iterations, which is kind of like, what are you doing, right? So like if your whole narrative here is that your self-improvement of LLMs, you created this self-play loop that allows LLMs to get better over time, why would you only run it for 2 iterations, right? Like, wouldn't you run it for 20 and 100 and 1,000? Like, if you can infinitely farm this, why did you only stop at 92, right? Like, what happens, right? So I think that even though these papers are very promising, I think the reality of this, the reason they only do 2 iterations is because the 3rd iteration made it worse and the 4th iteration made it worse. So there's some wall that they're running into that is why they're only showing you results up until 2 iterations, right? Because if they did 4 iterations and it worked better, they would have shown you that. If they did 10 iterations and it worked even better, they would have shown you that, right? So all these self-play papers with language models, they're just like, oh, we just did it for 2 tries and then we just left. It's like, what? That doesn't make any sense. You probably did it 10 iterations and 100 iterations, but because the results weren't good, that's why you're probably not showing it to us. Okay. Models trained on trajectories from re-ranking MCTS outperform the initial policy. Self-improving has the potential to achieve continual performance gain. Limitations. Although Alpha LLM demonstrates improvements over base models, its performance in gradient sampling is substantially inferior to that observed when decoding with MCTS, right? So it's like the language model itself is not that much smarter. It's really this combination with this search through a tree, which is MCTS, that makes it good. In our existing framework, the critic models remain static. So that's an important point, right? These critics here, the value function, the PRM, the ORM, right? For all 3 of these, they're basically just taking the policy and then adding a little MLP on top, right? It's only the MLP that is receiving gradient. So even though here they have a loss and they're saying, oh, we're training the value function with this loss, the loss is only going as far as the MLP, right? So the actual policy itself, there's a stop gradient there. It's not actually, the policy is effectively frozen. So one of the limitations and one of the things that they wish that they would have done here is like, okay, well, what if we allowed the gradient to flow into the policy itself, right? And this will ensure that the discriminator-generator gap and improve overall training dynamics. And here, they're kind of making a reference to the generative adversarial networks. So generative adversarial networks have kind of fallen away, you know, like people don't really think about them too much anymore. But one of the things with GANs was that they were very difficult to train because you had this generator network, which is basically generating an image, and then you have a discriminator, which is determining whether that image is real or fake. But over the course of training, you want the generator and the discriminator to basically be roughly the same. You don't want the discriminator to be much stronger than the generator or the generator to be much stronger than the discriminator. So balancing the training dynamics in the generative adversarial network was difficult because of that discriminator-generator gap. And they theorize here that, okay, if we could push gradients into the critic and into the actor, that would probably make the overall training dynamics better. And the overall training dynamics is probably why they don't get results better than just 2 iterations, right? So maybe if they could push gradients into the critic, they would be able to run this for more than 2 iterations and see continual improvement. And that's basically it, guys. That's this paper. Pretty neat little paper by Tencent here towards self-improving of LLMs via imagination, searching, and criticizing. And now we're going to go to our next paper. I'm going to take a short little water break here. You guys are having a nice little lively discussion there. Is there some of this magic also done to the base models? So the base models are the pre-trained language models, and they've just been trained to just predict the next token in a way that is statistically likely based on the giant amount of pre-training data. So part of the reason people use RLHF is also to elicit this kind of chat behavior, right? So the primary use of RLHF is to make a language model behave like a chatbot, right? So the instruction tuning data set is almost always to make it behave like Like, I'm going to say something, and then you're going to say something, and then I'm going to say something, and then you're going to say something, and you're going to sound like a little human that's answering me, right? Versus a base model or a pre-trained model, it's just going to output tokens. Like, it's just going to like pretend that you're giving it the first half of a paragraph, and it's going to give you the second half of the paragraph, right? Okay. So, second paper, R to Q star. Your language model is secretly a Q function. All right, and we're going to mention a couple things here. So the Q star, right? So this stream is called Q star. So there's a couple different possible interpretations of what this means, right? So Q definitely stands for the Q function, right? So that's kind of unmistakably, there's this Q function, Q learning, in reinforcement learning, that is unmistakably that. But I actually think that there's potentially, like, the star there could mean a couple different things. So on one hand, Q star, if you're constraining yourself to reinforcement learning terminology, Q star stands specifically for, let me see if I can find it. Yeah, Q star is the optimal Q function. So there's some Q function that you have, and that Q is an estimate of the you want that Q to ultimately become the optimal Q function. So if you had some God level Q function, that would be Q star, right? So maybe Q star refers to the fact that it's a Q function that's optimal, right? But I have another secret theory here, and this one is like, I'm not saying this is it, this is just my own theory, but I think that the star might refer to A star. A star is a search algorithm that is very, very popular, right? So if you guys have ever done any kind of LEET code, right, when you guys are applying to your tech jobs, half of the problems end up being some kind of graph search, right? And you're either doing breadth first search or depth first search, right? So beam search, which is a type of decoding, is basically just this kind of search algorithm, right? A star is also a kind of search algorithm. MCTS is also kind of the same thing, right? So all of these words, even though there's specific formal definitions for them, and someone who's like an RL PhD will be very offended by the fact that I'm calling A star and MCTS the same thing, they're basically the same thing, right? But A star is pretty good. This is what A star looks like when it's searching through a maze. So maybe if you do LLMs and instead of MCTS, you have a little A star flavor in there, maybe that's where that star comes from. Maybe it's more, hey, we have Q learning with A star baked in, and that's what Q star stands for. So that's kind of my secret conspiracy theory, but more often, the much higher probability outcome is that Q star refers to the fact that Q star is the optimal Q function, right? But I don't know, I just kind of wanted to throw that one out there. Okay. What else? Another thing I wanted to mention here, so from R to Q star, this is Chelsea Finn is the advisor here. Chelsea Finn actually recently dropped out. So you had a bunch of the high-level people at Google, including these guys, Sergey, Chelsea. These guys are boss mode, like these people are some of the most influential and like kind of knowledgeable people in reinforcement learning and reinforcement learning for robotics. And then both of them, including I worked under this guy. I didn't quite work under these guys, but I've met them and they're pretty good. They made their own general purpose embodied robot stuff. So everyone and their mother is making humanoid companies, and all the people involved in these papers are making humanoid companies. So pretty much all the best talent in the world right now is working on embodied intelligence. And I don't know, to me, that just means that we're literally just a couple years away from humanoid robots that work in your house. And I know that's kind of a crazy prediction, but I just don't see how it doesn't end up that way. Okay. People weren't dropping out of Google to make autonomous vehicle companies, right? But people are dropping out of Google to make humanoid companies. It's a difference. Humanoid stuff somehow involves Q star. Yeah, I mean, this stuff is all directly applicable to robotics as well, right? So you can envision that you could do this, but rather than tokens and language, you do it in action tokens, right? So one way to think about where robotics is going is that the robot policy is outputting tokens and is starting from a pre-trained language model. So the robot policy itself, and this is the kind of follows the vein of research of the RT2, RTX, which is robotic transformers, which come from Google, where they're basically saying, okay, rather than training these little multi-layer perceptrons from scratch, which is what people have been doing in robotics, right? Why don't we just take a pre-trained language model, and the pre-trained language model outputs robot actions? Okay, well, if the pre-trained language model is outputting robot actions, isn't robotics kind of more similar to math and programming? Isn't robotics something where you can get a, let me go back. Boom, boom, boom. Yeah, isn't robotics something where you can get the final answer is correct or wrong? That's the case, right? In robotics, if I'm performing some grasp, or if I'm moving something, or I'm trying to grab something, I know whether I grabbed it or not, right? So if I know the final answer is correct or wrong, I can create a robotic transformer that outputs action tokens that uses a self-play loop like this to basically get better and better and better and better and better and better and better, right? There's no limit to it. It's not like just generic natural language reasoning where it's impossible to get a very high quality reward signal. I think in robotics, you can get a very high quality reward signal, which means that you can use this type of strategy, which means that the people who are working on these things, like Chelsea Finn, came to this realization and were like, holy shit, we can actually do this. There's no limit to this. We're going to be able to create a self-play loop with a transformer that has been pre-trained that is now outputting robot actions in order to create human level and superhuman level embodied AGI. And they were sufficiently convinced about that they're dropping their probably multi-million-dollar pay packages at Google to make their own startup. And everyone is doing this. So get hyped. Yeah, if you can't see this on YouTube, I multicast to X, and then I also multicast to Twitch. So you can go to either of those platforms. I have it written down here. X, Twitch, and YouTube, whichever one you want the most. But I only look at the comments on YouTube. So if you send stuff on Twitch or X, I'm not going to be able to see your comments. Okay. Let's go through this paper. This paper is a little bit, it's not as cool as this one because it's kind of a little bit more mathy, but not in like a good way. So standard RLHF deploys reinforcement learning in a specific token level MDP. So token level MDP, that's referring to what we were looking at before, right? Where you basically, are you doing the Markov decision process at the token level, or are you doing it at the sentence level or the option level? DPO is derived as a bandit problem in which the whole response of the model is treated as a single arm. So DPO is, we actually, I think, also read this paper, but it's kind of a different type of RLHF where you're doing direct preference optimization. And what they mean here by a bandit problem is a reference to this. So the bandit problem is a reinforcement learning kind of idea where these are called bandits. So a bandit is like an English word for someone who like steals from people, right? Like a bandito. But these like machines where you like pull the arm, right? They have a little arm and you pull it and then they like kind of like randomly spin and then they give you money or they don't give you money. Those are called one-armed bandits, right? So you can envision that the people who are good at these machines, if they exist, one thing that they do is they don't really play with the same machine every time, right? They have multiple machines in front of them, and then they kind of like try out each one. And then over time, they build this kind of intuition about, okay, this machine, this one here, this one actually seems to give me better scores than this one here, right? So they're building this intuition about which machines are good and which machines are bad. And that's kind of the multi-bandit problem, is basically saying, okay, I have some prior belief about what each of these machines is going to give me. So here's my prior. I'm just going to start with a Gaussian distribution for each of these. And then as I collect more experience, as I keep pulling on these, I'm going to improve and get a better and better estimate of what the true probability distribution for the expected reward of each of these bandits are, right? So the multi-bandit problem is basically, okay, given a finite number of these pulls, as in I'm like pulling and trying out each of these individual bandits, how can I optimize my winning? How much should I explore? How much should I exploit? Blah, blah, blah. So it's kind of like the multi-bandit problem is just a reinforcement learning kind of terminology referring to this idea of like, I don't know which of these things is better, but I can slowly over time, by collecting experience, get an idea of what the probabilities for each of these are and shape those with data. And here what they're saying is that in DPO, the whole response of the model is treated as a single arm. So in RLHF, you're doing a token level MDP. So in RLHF, you're looking at each individual token, and your MDP is saying, okay, here I have some individual action that takes me to the next token, next token, next token, versus DPO is more the whole response. So DPO is kind of more like this, where you're evaluating the entire response given the entire input. Okay. In this paper, they theoretically show that DPO and the token level MDP is effectively the Q-learning algorithm and satisfies the Bellman equation. Because of its token level interpretation, DPO is able to perform some type of credit assignment, aka it is Q-learning. Classical search-based algorithms, such as MCTS, are equivalent to likelihood-based search on a DPO policy. Simple beam search yields meaningful improvement over the base DPO policy. And this sentence right here, simple beam search yields meaningful improvement over the base DPO policy. Beam search is just this, right? It's just searching through that tree. So beam search is better than the base policy. Where have we heard that before? Right here. Look at that. Beam search, which is kind of similar-ish to this MCTS, you're going to get a way higher score using that than you are with just greedy. So we're seeing a lot of agreement. Both of these papers are basically kind of saying the same thing, right? Okay. Classic RLHF methods optimize token level value functions with a sparse reward at the terminal state, right? So this idea of you have token level value functions, you're evaluating at every single token, and your reward comes at the very end. So in RLHF, you have some expert data, and you're basically saying, okay, this was the question that the person asked, here's the response, and then we know at the very end of the response, that was the correct response. So then we're gonna go back through all the tokens that it took us to get to that very final answer, and we're gonna assign some discounted reward to that, and that's how you kind of get your reinforcement learning from that. Okay. DPO, on the other hand, operates in a contextual bandit setting, treating the entire response as a single arm. Blah, blah, blah. We skipped the related work, the introduction. We got stuff to do. So they also have their own kind of definition of reinforcement learning. Pretty much any reinforcement learning paper is going to start with a definition of the Markov decision process. They have their own version of that, so we're going to kind of skip that. Token level MDP. In RLHF, the reward function is learned from human feedback over preferences between responses, which we denote using as trajectories at the token level. So this is like, the terminology here sounds confusing because they're trying to marry the terminology from two different things, right? So in language models world, we usually talk about input sequences such as X and then an output sequence such as Y, right? So you're trying to go from some input sequence X to some output sequence Y. But in reinforcement learning, so in reinforcement learning literature, you're more so describing these states, and then you have actions, and then you're taking an action to go to the next state. And then, so even though fundamentally what you're doing is the same exact thing, which is effectively what this paper and this paper say, right? Like in this paper, they say the same thing, right? Like this therefore constitutes a Markov process. So both of these papers are telling you that, like, yeah, they're different terminology coming from different areas of research, but ultimately a language model can be thought of as a policy that is executing some Markov decision process. And these guys are basically saying the same thing, and they're going beyond that as well, right? So this paper is all about basically saying that whenever you're training a language model and pushing gradients using DPO or RLHF, that's actually very, very similar to what you do in reinforcement learning, where you have these trajectories of state and actions, right? Except here, we usually just call them a sequence of output tokens. We don't call it a trajectory of tokens, but trajectory and sequence is just two words for the same thing, right? It's just an ordered list of things. Okay. Blah, blah, blah. Classic RLHF. Policy gradient methods like PPO. KL constrained, RL objective, KL, the KL divergence. KL divergence is a metric for probability distributions that basically says we're going to try to maximize. So we're going to try to maximize the policy. So the policy that maximizes the action given a specific state, right? This is your policy, pi theta is your policy. That policy is trying to maximize the reward, so how much reward it's going to get from this trajectory, but it's also penalized if it strays too far from this reference policy, right? And this is the P in the PPO. So PO is proximal policy optimization, I think, and that P, the proximal, stands from the fact that you're trying not to venture too far off from the current policy. So your reference policy, you have this KL penalty there that prevents it from drifting too far away from the current policy, because if you drift too far away, you're now in a new area of state action space that you haven't really efficiently explored, and the value function there is not going to be very well defined. You're going to be doing weird shit that you don't know what's going on. So you're better off just kind of like staying within a little area, little bounded area based on this beta parameter here of how close you are to your reference policy. Okay. Here's your reward. Your actual reward using the token level PPO is at the very end. You have your final reward, and then you basically propagate that all the way back for all these states in your trajectory. Okay. DPO, here's another definition of DPO. You have the same kind of things here. Here's your policy, pi0, which is outputting some sequence Y given some input sequence X, right? So this is kind of what this whole paper is trying to prove, that they're really the same thing, right? So they're trying to make you realize that even though we have, in language model world, we call things Ys and X's, and here in RL world, we call these things states and actions, like it's kind of the same shit, right? Like these Ys, these X's, fundamentally you have these reference policies and you have your policy, and then you're trying to push gradients into the policy so that it takes better actions, or in language model terminology, so that it picks better tokens. Okay. Here's your Q star, which is trying to give you the reward for a given XY tuple, where X is the input, Y is the output. So the Q star will give you the reward of that output given a specific input. Pi star is the optimal policy. So the pi star gives you an action conditioned on some state, and the Q star will give you the value, or the kind of like how good that specific state action tuple is, right? And you don't know what pi star is, and you don't know what Q star is. They're the optimal one. They're the ones that you want to get to. Your goal with reinforcement learning is to get to a point where your pi star is the optimal, where your pi is the pi star, and where your Q is the Q star. But you don't know what those are, so you're kind of estimating those and getting better and better estimates over time. Here's the relationship between the value function and the Q. So you can see how the value function is just basically the Q, but with these little betas here and integral over all actions. Optimal policy optimizes for future returns. Here's a little spelling mistake for you guys. I think this is also a spelling mistake. Bellman, that should be capitalized, and I think there's only one M. Is there only one M? Yeah, look at that. Bellman equation. 2 L's, 1 M, and it's equation. And then here, they misspell it. Bellman. Lowercase, 1 L, 2 M's. I love finding spelling mistakes. It makes me feel like I'm doing something. All right, here, as I said, this paper is very mathy, so here's their conclusion. Lemma 1, under mild assumptions, there is a bijection between reward functions and corresponding optimal Q functions in the token level MDP. Bijection is just a fancy mathematical way to say a function that has one-to-one and maps onto the other thing. So you can see that here, it's not one-to-one, and they don't map directly. So here you're missing the 4. Here there's 2 of them mapping to the 2. Here you're missing the 3. So bijective mapping between reward functions and optimal Q functions basically means that these are kind of the same thing. An LLM is always the optimal soft Q function for some reward function in the token MDP. Okay, so the LLM is a Q function. As they say in this paper, your language model is secretly a Q function. You just need to reframe the terminology in your head in order to realize that. Blah, blah, blah. More proof in case you didn't believe them. This theorem implies that we can use DPO to learn the optimal policy for any per token reward function. So what if we used DPO to learn the optimal policy for something that wasn't math and programming, right? So if we can figure out a way to learn a value function that can be used here, right? So here they don't really train, the value functions that they use here are specific to coding and math, and they're getting better, and they're not even pushing gradient into these, right? But what if we could create critics that were based on something else that is not math and programming, and then use those as basically the value functions to evaluate our MCTS, which is where I think this all leads. How do we fine-tune LLMs such that it is the optimal Q function? Blah, blah, blah. Look at this. This is absolutely insane math here. But really what they want you to... all that math is just to say this, right? Two reward functions, R and R prime, are equivalent if there exists a potential function such that R prime equals R plus phi. And then we're going to learn that phi, I guess. Given a reference policy and a parameter, all reward classes consistent with the placket loose can be represented with the A reparameterization of this form. Okay, so here's your reward S of A is your policy. So whatever your policy is telling you here, and then you have your reference policy there, which is usually just the policy but the previous one. This theorem implies that we can use DPO to learn the optimal policy for any per token reward function. While this interpretation does not generally hold in continuous spaces, but we're lucky because natural language is actually a discrete space, right? Natural language, there's a limited set of tokens that you can output at every single step, right? Every action is limited to an action space of whatever your vocabulary is for your language model. So technically, natural language is discrete, not continuous. And even things like robotic control can be made discrete, right? Robotic control, you can think of it like continuous and say, okay, this joint can be anywhere from 0 to 1 or -1 to 1, and that's a continuous space. But you could also discretize or bin that space into specific, maybe 256 bins, right? And then in that case, then the action space for your robot is now discrete. And discrete spaces generally much better than action or continuous spaces. Okay. In terms of the actual results for this paper, they really just use very tiny models and a very tiny data set. So they use the Pythia 2.8b model with the Reddit TLDR summarization data set, because the point of this paper is not to beat a benchmark, right? So in this paper here, this is the Tencent paper, they ultimately want to beat the benchmark, right? They want to show you that they can use this self-play loop with a Llama 270B to ultimately get to the point of a GPT-4 level performance. But this paper is not that type of paper. In this paper, what they're trying to do, this is more like a math theory paper, and really what they're doing is they're trying to show you a bunch of math and kind of a bunch of proofs here just to make you realize that a lot of the stuff that we're dealing with in reinforcement learning can be directly applied to a lot of the stuff that we're doing in language models, and that really these are just two sides of the same coin, right? Okay. Model successfully identifies the tokens corresponding to the erroneous statements. It can do credit assignment. So here they're kind of trying to show you that I think the way that this works is that there's basically errors. So here, for example, in this paragraph, the 250K here is an error, and the model itself learns to kind of ignore that 250K. So in a way, it ignores specific things. I don't exactly know, but the credit assignment refers to the problem of knowing who gets credit, right? So the credit assignment, for example, in the game of Go, is that you only have the reward signal at the very end, right? You have the reward, I won the game at the very end, but that game was 100 moves. So even though I won the game at the very end, which of the moves that I took are the ones that deserve the most credit, right? So like, how do I assign credit to the moves that were good if all I have is just the signal at the very, very end, which is I won the game or I lost the game, right? So that's the credit assignment problem. And in the natural language world, you also have this credit assignment problem of like, okay, you're asking me some question, I'm producing a bunch of tokens, I'm producing this trajectory of tokens and ultimately getting the question right or question wrong. How do I know which of the tokens are the tokens that actually helped and which of the tokens are the tokens that didn't help, right? So if you feed this into the language model and you're looking at basically the attention or how much emphasis that's putting on each of these tokens, and it's ignoring some tokens and then looking at tokens that are good, then that means it knows how to do credit assignment, right? It knows how to say, okay, at the very end, this was a good answer, but not only do I know that it's a good answer, but I know which of the tokens in this token trajectory actually deserve more credit than the other ones. All right. And if you can do that, then this is a promising sign of the ability to do stitching or combinatorial generalization from offline data. And what they're referring to here is that there's kind of a problem with reinforcement learning as it used to be, because a lot of reinforcement learning needs to be online. So online reinforcement learning means that the data is fresh, right? You're basically using data that you collected with the policy itself, the policy that you're going to end up pushing gradients on, right? But offline reinforcement learning says, okay, well, actually, we'd like to be able to use this much larger amount of data that might have been collected by something that wasn't the policy at all, right? So in that case, you have a lot more data, but the data wasn't collected with the policy that you're using and you're trying to push gradients into. So if you could figure out how to push gradients from this larger bin of offline data, that's going to be pretty good. And if you can figure out how to do that while doing credit assignment correctly, now you're cooking, right? Because now you're like, okay, not only is this data from a completely different robot, but I know specifically which tokens in that robot trajectory that ended up succeeding are the tokens that were correct, right? The action tokens that actually led to the thing being correct. So credit assignment plus the ability to use this offline data is very powerful, and that's why these guys are making their own startup. Okay. Our findings could be significant for the use of reinforcement learning and RLHF and LLMs, and could be very, very good for robotics. Okay, connecting guided decoding. Guided decoding is basically this, right? So guided decoding is anything that isn't greedy. I guess sampling maybe counts as guided decoding, probably not. I would say MCTS, beam search, any kind of like graph searching variant counts as guided decoding. A-star, maybe. During inference time, they deploy a graph search algorithm in the token MDP. So the MDP that's operating at the token, you deploy a graph search algorithm such as MCTS. Blah, blah, blah. I think none of these are necessarily worth looking into. A surface level interpretation would lead one to believe it increases the likelihood of chosen responses while decreasing the likelihood of rejected responses. This, however, does not account for a well-observed phenomenon in which the likelihood of the chosen responses actually decreases over time. So this is kind of like a weird thing that people noticed, where apparently when you fine-tune a model with direct preference optimization, the responses that you are directly optimizing with, right, the expert responses of like, this is my direct preference and I want you to push a gradient based on this direct response, right? DPO, you're pushing the entire response, right? It's not token level. But something that's weird is the likelihood of that actual response decreases as you push gradients for it. And people were like, what the fuck? That doesn't make any sense. But if we now take all that we've proven in this paper, which is realize that all of these concepts in DPO and LLMs are really just the same concepts that we've been looking at in reinforcement learning and maximum entropy reinforcement learning, then this actually does make sense. And that is kind of one way that they use to justify this paper, right? So they have their theoretical mathy kind of proof justifications, right? Where they say, okay, here's your, oh, look, it kind of looks like the Bellman equation. But then they also say that our reframing of LLMs and MDPs, or LLMs and DPO, is actually explains one of these weird nuances that people ran into when trying to use DPO. So in that way, here's two different kind of data points that show that your language model is secretly a Q function. All right. That's most of that. The likelihood of the chosen response should decrease, blah, blah, blah. Exhibit characteristics, namely that the implied Q function monotonically increases over time, right? You want that Q function to give you higher and higher scores, right? It knows which scores are good. We formulated the DPO optimization as learning an optimal Q function, which is represented by an LLM. We provide theoretical justification for empirically observed DPO training phenomena. We show comparable empirical gains by a simple one-line code change using beam search. So that's what we were looking at before, where you can just use these searches when you're doing decoding, and it'll drastically improve your performance. Qualitative early signs that DPO is able to learn credit assignment directly from feedback data, which then kind of opens the door for potentially training more interesting things. And if you can get a very, very good value function or something that can do this credit assignment and ultimately label your tree for you, right? If you have something that's very, very good at giving you the value for each trajectory in token space, then you can use that to get a very, very good policy, right? So if you can get a good critic, you can get a good actor. And in any kind of actor-critic kind of self-play loop like that, you need them both to improve. So you need to have a way to improve the critic, and you need to have a way to improve the actor. Learning reasoning from feedback, sampling multiple reasoning chains, and iteratively fine-tuning on the ones that provide correct answers. This is potential future situations. And then agentic LLMs. DPO training on the full model trajectories could learn optimal exploration behavior. So optimal exploration behavior, you could think of that at the token level, right? And you're like, okay, well, our LLMs are just going to be better at producing sentences and tokens. Or if you're thinking about LLM agents, such as WebGPT, but also such as a robot, such as an embodied humanoid robot, then optimal exploration behavior and getting good trajectories on a robot, now we're talking. Using LLM as a prompt refiner and generator, improving the prompt drafter and image generation directly. So they do have some examples here of how you can use this to basically improve the generation of text, or improve the text that you can then use to generate images. So right now we're in a world where generating images with these generative image models is kind of like is difficult because you have to create a good prompt, right? So there's this kind of like prompt engineering. But if we can use DPO to basically evaluate trajectories, then we can try a bunch of different prompts, evaluate each of those prompts, and then ultimately get prompts that are better than this, right? So you're using the DPO value function or Q function to improve your prompts because it can tell you how good a specific trajectory of tokens is. And that's pretty much it. Volkswagen. Do you think Volkswagen even knows what they're doing? You know, do you think Volkswagen is aware that they're funding research on Q-Star? Not that that's nefarious or anything. I think this research is like very vanilla, but you know, they're just like pissing money away. All right, guys, that's pretty much it. Those are the two papers I wanted to go into. I'm going to take some water here. You guys ask some questions, and then we will, I'll do a little summary. Vegas. I've only been to Vegas once, and it was terrible. Everything was super expensive. It was just filled with like kind of like people that are like gambling addicts and kind of like depressed. I don't know. I don't know. Maybe I just did it wrong. Maybe I have no idea how to do Vegas, but Vegas is definitely overhyped. What's the best tutorial on DPO? I think if you're interested in DPO, you should probably read the original paper. I think I have a stream on it, so you can do that. But then just look for an implementation. DPO GitHub. Yeah, here you go. So let's see. You got this guy, and then you got this guy. So let's see. Let's compare these. This is a Apache 2 license. That's good. 1.6 stars. Very good. And then let's look at this one. Apache 2 license. That's good. 10 stars. Not very good. Okay, so probably you want to look at this one. Eric Mitchell's implementation of direct preference optimization. So you come here, run this crap here, look through this train.py, look through this preference dataset.py. I think like jumping into code like this is probably the best way to learn about a specific technique. But if you want to have a more theoretical kind of back to it, you can read the paper and then look at the code or kind of look at both of them at the same time, and so on. Why would they not? What do I do for a living? I write software. Why would they not? They have enough money to spend. Maybe, I don't know. Like, I mean, Tesla fired a bunch of people. It seems like Tesla is way more efficient with its capital than any of the other car companies. So it's weird to me that car companies such as Volkswagen are like just bleeding money like everywhere into all kinds of bullshit, and none of it, you know what I'm saying? Like, it seems like they should be much more efficient. Breath and air. I've heard of DSPY, but here, let me make sure I'm thinking about the right thing. Framework, you see the link is purple. Let's see. Framework for programming, not prompting foundation models. Algorithmically optimizing LLM prompts. Separates the flow from the parameters. LM-driven algorithms that can tune the prompts and are weights of your LLM calls, given some metric. Okay, so it's basically like programmatically trying different things. Much more reliable, higher quality. Yeah, I mean, this is probably fine. The problem is that this is not guided by anything, right? So it seems like this is basically similar to like a kind of a search-based strategy, right? So you're kind of searching through the space of possible prompts, but what are you actually using to search that space effectively, right? In this case, the only thing you end up having is this metric. So you're defining some metric, and that metric ends up telling you, okay, out of all these different things that I found, all these different prompts, this is the one that is best. But that's never going to be as good as something like this, right? Something like this is way more efficient because you have a value function that you can use to evaluate like these prompts, and that value function is much more fuzzy, right? Like I don't know what the weight metric here is, but the metric here is probably some hard-coded human thing. So you're evaluating kind of your search over all possible prompts based on this random metric that you design, so you're going to kind of live and die by that metric. Versus here, you're creating these language models which are much more fuzzy and ultimately give you some reward. And not only that, but you're also exploring much larger possible spaces because you're using these fast rollout with specialized LLM. So you're exploring a much larger search space and then using, I think, a better value function to evaluate the possible trajectories versus this is probably more kind of brute forcey. But I haven't actually used this, so I don't know. Maybe it's great. I don't know. I don't want to necessarily shit on it without trying it, but that would be my kind of intuition, is that it probably is just kind of brute forcey and like we need to kind of do something more like this in order to get better. DSPy is guided with some examples you provide. Okay, so actually maybe DSPy is more similar to this, right? Because DPO, direct preference optimization, the way it works is it's using like a little data set of preferences, which is basically given this input, I want this output. Given this input, I want this output. So, okay, so you're saying DSPy is actually very similar to what they're doing, is basically DPO. What is your view on the current job market? It's pretty brutal. You know? I think it's like, it's not. The problem is that the macro environment is not looking good, right? The macro environment is based on these like central banks and whether or not they are basically when the central banks decide that interest rates are going to be low, that means that there's more money flowing in the system. So people are more likely to fund startups, right? People are going to spend more money on startups, which means that startups are going to hire more people. When the central bank decides that they want to keep rates higher, it means that people don't want to put their money into investments. And it also means that companies are evaluated based on their ability to get money. So they're going to start firing. So right now you have a kind of a situation where no one's hiring and startups aren't getting a lot of money. So there's not a lot of jobs. And because everyone's firing people, now not only is there not a lot of jobs, but you're also competing against a lot of people. Right, especially like people with like Google on their resume, people with Meta on their resume. So like, it's a very, very difficult environment to try to find a job. So it's not looking good, but unfortunately, the only thing you can do is just kind of wait. So you can continue to build your skill set, and then hopefully maybe a year from now you can get the kind of AI job that you want, or you can try to find a job in something that is a little bit more in demand. I don't know, maybe like restaurant worker or something, but I know that that's not really what people want to work in. Decision trees kind of attach some value at every node. Or MCTS or DPO working in the same way? Decision trees are not MCTS or DPO. Decision tree is like kind of like a old type of machine learning model, but there is a similarity there between the fact that it's a tree, right? In a decision tree, you have the same kind of a tree kind of structure, and you're making decisions at the nodes and then ultimately ending up at something. So yeah, the tree part of that is similar-y, but in terms of like the actual what they are, MCTS is not a decision tree. Is DPO a bit like overfitting on something you want? Kind of, yeah. At some point, you're going to overfit, right? So like that's really what I think happens here, right? That's why I think that if you don't do, if your DPO is being treated as your Q star, right? So if your DPO is effectively like your optimal Q, you're going to be limited by the quality of that DPO data set, right? So at some point, you're going to iterate, you're going to do this self-play enough times that you're going to start to overfit to that DPO data set. At some point, you're going to be pushing so many gradients based on this little DPO data set that it's your model's going to almost start trying to overfit, and overfitting in this case might be like literally matching the exact sentences. So it wants to output that exact sentence, right? Something like that. You can definitely overfit. Anytime you train and you keep pushing gradients based on some small data set, you're going to start overfitting. DSPy came much earlier than DPO. Okay. Does self-improving paper approach touch the model's tokenizer during self-improvement? No, the tokenizer is going to be fixed. Do I do corporate trainings? No, but if you pay me a bunch of money, I'll do everything short of anything creepy. I'm not going to like poop on your chest, but you know, if you give me enough money, I'll do pretty much anything. Maybe you get one trait and then it interferes. YouTube comments are working finely. Good evening. How's it going, Kalina? Any recommendations on getting started with machine learning for the unexperienced? Yeah, people ask that question a lot, but there really isn't any good recommendations. You just got to put a bunch of time into it. You know what I'm saying? It's like, it's just, your skill is just an integral of the effort that you've put over time. And people try to overfit and they're like, okay, well, if I can just, there's this kind of myth that like I can learn something in 10 hours if I'm just very good at the things that I'm learning, right? If I can just look at the study sheet, then I can learn it in 10 hours. So I don't want to waste my time learning the wrong things, but that's not actually true. That's a myth. Like 100 hours doing the wrong quote unquote things, you're going to end up more knowledgeable than 10 hours just like reviewing this like very specific like study guide, right? So I don't know, don't worry too much about what am I learning, and worry more about like, how can I just increase the total raw amount of hours that I spent on this thing? Yeah, just build something. That's a good idea. Okay. All right, guys, I do need to leave. I'm already over budget, so I'm going to do like a quick little summary here. All right, so here's the summary. Today in the stream, we tried to basically dive a little bit deeper on Q-Star and what it could be. Q-Star is a rumored algorithm that everyone at OpenAI is being secretive about, right? Sam Altman does not want you to talk about it, which means, in the words of Peter Dinklage, right? If you cut out a man's tongue, you worry only, you're telling me that you worry about what he might say, right? So in this case, if Sam Altman got Ilya to basically shut the fuck up about Q-Star, it's probably something good about it. So Q-Star, as Jan LeCun says, everyone really knows what this is, right? Anybody who's been in reinforcement learning, you pretty much kind of know what this is. Q-Star is, according to Jan LeCun himself, even though he doesn't seem to agree with this anymore, right? He's saying agency can't be a wart on top of autoregressive LLMs. Well, Mr. Jan LeCun, that's exactly what you described it as. So if the autoregressive LLM is this supervised, self-supervised learning, and then the instruction tuning data set is the supervised learning, then Q-Star is really just that little cherry on top. And what is that little cherry on top? Well, we have two papers that we went through that kind of maybe hint at what it might be. We have one paper from Tencent AI Lab people called Towards Self-Improvement of LLMs via Imagination, Searching, and Criticizing. In this paper, what they do is they basically combine a pre-trained language model, specifically a Llama 2 model. Where is it? A Llama 270B. And they get it to basically perform much, much stronger on these math data sets, specifically GSM-8K and math. And they do this by utilizing AlphaGo's self-learning kind of loop. AlphaGo is the pinnacle of reinforcement learning, the biggest success story around. I highly recommend the YouTube video where they show you this. But the key success to AlphaGo was the ability to use self-play to collect experience or a data set that it can then use to further improve the policy or the actual model that is taking actions in some space. So in order to do that, you're basically doing these tree search type of approaches. And in tree search, and one such type of tree search is MCTS or Monte Carlo tree search, you're looking at where you are in your board game, right? And you're taking a specific action. In the case of board games, it's a very obvious kind of thing. You're just basically, you're in a state and you take an action, which is just putting down a little chip, right? That's how Go works. So it's a very small little search space, small little action space, small with asterisks around it. Language is a little bit more complicated. In language, you can either kind of naively think about it being a Markov decision problem at the token level, but you can also be more fancy than that and think about whole responses as the actions, or even kind of this fancy option level stuff they do in this paper where they have like a secondary model that kind of basically decides when to terminate. But long story short, what you're doing is you're kind of expanding the tree of possible futures of like, here's the possible things I could do. And then you have some function or a different language model in this case that is giving you a value or a reward or some kind of number that is telling you, okay, this move, and then if I take this, if I say this token and then say this token and then say this token, my expected value of that is 0.8. And if I do this token and this token and this token, the expected value of that is 0.1. So like, I have an ability to look at all the possible things I can do and then tell you which one of those paths or which one of those trajectories is good and which ones are bad. So people have been doing this in deep reinforcement learning for a long time, but now with language models, people have basically replaced all the different parts of deep reinforcement learning with language models. So now we're using a language model for the policy, and we're using a language model for the critic or the different value functions. There's a couple different value functions that they try here, just kind of a vanilla one. They have a PRM, they have an ORM, but ultimately, these value functions are going to allow you to do this kind of tree search and collect data. Ultimately, that data, you can use it to fine-tune your model, and then you get a new updated policy, and that new updated policy is going to be better than your old policy. So this self-play loop resulted in a better model, and this type of self-play loop is how we're going to get superhuman performance, and we can do that right now because in coding and math, the final answer is correct, right? We know, much like Go, whether you won the game or whether you got the question correct, but it's still not certain whether you will be able to do this for all things. And my conspiracy theory is that Ilya figured out how to solve that problem. I don't know how he did it, but I think he figured out a way to extend this type of like MCTS and value function stuff to beyond just coding and math where you have this final answer. I don't know what that means, but that would be the coolest universe, right? That's if GPT-5 is Q star and GPT-5 is 100 times better than GPT-4, that happened. He figured out how to do that. If GPT-5 is just marginally better than GPT-4, he didn't figure out how to do that, and Q star is effectively just Ilya's implementation of this paper. So that would be kind of not hype. Blah, blah, blah. Ultimately, they get pretty good results. But I guess one more important thing to mention here, the results work a lot better. It's not like you're necessarily improving the language model itself. The language model itself, if you use it in a greedy decoding, which means just taking the token that is the highest likelihood every time, right? It's not actually going to be that much better than what it used to be as a Llama 270B vanilla. You actually have to do this MCTS on inference, right? You actually have to do this guided decoding in order to get to the performance of GPT-4. So a little bit of caveat, but I bet you that your language models a year from now, when you're interacting with it via some product, I bet you they're going to be doing some kind of MCTS in the background. You're not going to be aware that they're doing that, but they're going to be doing some amount of that just because the performance jump there is huge. All right. What else? We had AlphaGo, we had MCTS, definition of PRM, ORM, definition of PAL, chain of thought. This was the second paper that we looked at. This paper is more of a theory paper. They kind of basically go to show you, provide some theoretical justifications, provide some more empirical observations that demonstrate that a lot of this DPO, RLHF that you're doing with language models is very, very similar to what you're doing in reinforcement learning. Effectively, these are the same things. And as they put it in this paper, your language model is secretly a Q function. Multi-armed bandits, beam search, A-star. And yeah, people believe in this enough that they're basically fucking making their own startups. So as I said before, people weren't dropping out of Google to do autonomous vehicle startups, but they're dropping out of Google to do humanoid startups. So they know something that we don't know. But even just based on these papers, it seems like this stuff works pretty well. So that's pretty much it, guys. That's what QStar is. That's my best guess. Hope you kind of know and have a better intuition. Maybe next time you're talking to your friends, you can have a better idea of what QStar is and impress them with your reinforcement learning knowledge. Literally hours. I need to leave right now, so I appreciate it. Thank you, everybody. Thank you, Kalina Work, Hamza, Jabali something, Luke, Iki, Spyro, Irabu, something again, Old Kips, Hamza, Luke, Tomcat, 87, Old Clips, D-Raj, Piotr, English, Eker, Hamza, Iki, Majetti, 2ARX, ORZ, Old Clips, CK2, Madlips, Jay, Sarah, Mamadisk, Jay again, Alex, Rian, Nash, Anestis, QD. Thanks everybody for joining. See you guys next weekend. Have a great rest of your weekend, and bye-bye.